So hello again. So here's another example of an optimization problem, and let's go ahead and try to solve this problem. So we are given the following text that we need to interpret, right? So let me just go ahead and make that text maybe a little bit larger. So I also wrote down the interpretation there. So there you go. All right, that's good enough. I guess you guys can see that. So see that. I got this example from a textbook, from another book, an optimization book actually. So here is the statement of the problem. So Öreg McDonald owns 1,000 acres of land and is contemplating conserving, farming, and or developing it. So he has three options in front of him. 1,000 acre land, which he can partition into three parts, for which he can use a portion of it for conserving, another part for farming, and the last part for developing it. His annual considerations are as follows. It will only cost him $1 per acre in registration fees to own conservation land, and he will reap $30 per acre in tax savings. So by just spending $1 per acre for a land which is allocated for conservation, he can get $30 net tax savings. So therefore, the net benefit to him would be $29. So the part of the land which is conserved, which is partitioned for conservation purposes, I just label it as X1. All right, so X1 is my variable which represents conserving. And then, how about farming? Farming will cost him $50 per acre for seeds, from which he can earn $190 per acre by selling vegetables. So by just spending $50 per acre, he can earn $190 per acre by selling vegetables as well. He can earn $290 and X2 as a result, the land, the amount of land. So let me just write it here. Amount or size of land dedicated for those activities, right? X2 is the size of the land dedicated for farming activities. And he can earn $290 per acre by renting developed land, which will cost him $85 per acre in permits. So the net benefit again would be $205 in that case. So Öreg has only $40,000 to use. That's it. That's his whole budget, $40,000. He has to be smart, so he has limited resources. And he's also bound by having only 75 descendants, each of whom can work at most 2,000 hours, right? So 75 times 2,000, I think it would make 150,000 hours of labor work available to him. How should he apportion his acreage in order to maximize profits if conservation, farming, and development uses 12, 240, and 180 hours per acre respectively? So this is a standard example of a constrained optimization problem, which is of a particular kind, which we call it as linear programming. And the reason is the following. So first we need to understand the objective function, and then we can look at the constraints. Later on we will realize that they satisfy a certain form, which leads us to the name linear programming. But first let's start with the objective function. So what is he trying to maximize or minimize? His objective is to maximize here profits. But how do we calculate profits? Well, it turns out that profits, remember, per acre, we know exactly the benefits of each of these three uses of the land. So per acre, if you are conserving the land, conservation, you just spend $1 per permit fees, registration fees, and as a result, you earn $30 in tax savings. So therefore, the net benefit to you is $29 per acre for every acre of land that you conserve, right? So $29 times X1. Do you guys see that? Plus, well, if you were to farm it, for farming you need $50 per acre of seeds, for which you can earn $190 per acre of selling vegetables, because you will grow vegetables. So the difference would be $140 per acre, but because you are farming X2 acres of land, X2 times 140 would be the second component. And finally, plus the last part is developing the land. If you develop it and then you rent it, the renting income will be $290. The expenses will be $85. The difference is $205. times the acres of land that you decided to develop, right? So therefore, this looks like a legitimate objective function. This is your profit function. Maximize 29x1 plus 140x2 plus 205x3, where x1, x2, and x3, they represent the size, the amount of the land which is dedicated for those three different causes. Conserving, farming, and developing. But there are some certain constraints that he's facing. First of all, he doesn't x1, x2, and x3 the way they are, it's not infinite. He doesn't own an infinite amount of land. In total, he owns 1,000 acres of lands. So the total of x1, x2, and x3, whatever they are, it has to be less than or equal to 1,000, right? So for instance, the sum here, if I were to add these three numbers, it's 170. So you guys have still some room for instance, we can have this one 300 and maybe this one 600. So this is within the boundary, right? But then wait a second, that's not the only constraint that our farmer is facing, Mr. McDonald is facing. He also have a second type of constraint, which is and the first constraint, by the way, is represented by this inequality here. The second type of constraint that he's facing is that he has only $40,000 to use. And in each of the three projects, he needs to make an initial spending before he can reap the benefits. In the first case, he needs to spend $1 on registration fees if he were to conserve the land. $1 per acre, but because he's conserving x1 acre, so 1 times x1. If he were to farm it, he needs to spend $50 per acre for seeds. But because he's farming x2 acres, x2 times 50, the initial spending. And finally, for the last allocation, in order to get that much rent, he needs to first of all spend some on permits, which will cost him $85 per acre. So 85 times x3. So this second constraint here is that the sum of these three numbers, x1 plus 50, x2 plus 85, x3, the initial spending on his part cannot exceed $40,000. And lastly, as it turns out, that even if you wanted to conserve, farm, and develop your land, there are some certain hours that you need to put into those projects per acre. So 12 hours of labor for conservation purposes per acre. Because we are conserving x1 acre of land, and for each acre of land conserved, we need 12 hours of labor, so 12x1. And similarly, 240x2 plus 180x3, so they cannot exceed 2,000 times 75, which is $150,000, and that's the last constraint. The question doesn't mention any other, but in fact, obviously, because x1, x2, x3 are actual amounts of land that you are allocating for conserving, farming, and developing purposes, they have to be non-negative, right? That's the last constraint. Now, what I need is, now that I know the equations that I'm facing, so my objective function is this one, 29x1 plus 140x2 plus 205x3. I want to maximize this subject to those four constraints. The top three of them are inequality constraints in one direction. The last one is inequalities in the other direction. But this one we know very well, Excel handles it pretty quickly actually. The last one is kind of redundant, right? So how do we express it in Excel? Very easy. Now that I know x1, x2, x3 are represented by these green areas, I can just keep changing these numbers, right? For instance, this is not attainable because the sum is exceeded already. And this one is, for instance, let's think about 200, 200, 600. So what I can do is I can write out these constraints inside these formulas here. So for instance, constraint 1 was that the sum of all the xi's was less than or equal to 1,000. So inside this here formula, I have the sum of those three land uses, right? So their sum. Versus in the second one, I have this equation here, x1 times 1, x2 times 50, this 1 times 50, and x3 times 85. And you can see inside this cell over here, 12 times x1 plus 240 times x2 plus 180 times x3. And we want to make sure that these satisfy certain constraints. For instance, is this a legitimate use of the land? No, because look at that. We are satisfying the first constraint, but the second and third constraints are already violated. Do you guys see that? Because this number was supposed to be less than or equal to 40,000, and this number was supposed to be less than or equal to 150. So this is not a good way to allocate the land. More like, for instance, how about now? 300, 300. Is this a good way to allocate the land? This is constraint is satisfied. Oh no, I'm still violating the second one. This one is also constraint satisfied. So the second one seems to be painful to try to satisfy, right? So I need to put probably more into x1, like into conserving, because it's so cheap to conserve. Now it's, oh well, we're still not satisfying. We satisfied the third and the first condition, but not the second, because it's still more than 40,000. So maybe how about this? 500 here, 200 here. Is this set? Yes. Now it's satisfied. But as a result, you guys can see that my maximum is significantly lower. Now all three conditions are satisfied, though there's a problem. These two are not satisfied with sharp inequalities, right? So can we do a little bit better? Probably, right? So maybe because it is the cheapest way, conserving the land is basically doing nothing, right? It's the cheapest one, but at the same time, this is the one which earns you the least amount of money. The one which earns you more money is farming, and ultimately the one which is the most profitable one is developing. So I want to allocate more of my land to developing than to conserving, right? This is a standard operations research problem from management science. Or industrial engineering, you might say, and this is a good application I thought that I wanted to share with you all. All right, so how do we solve this? Very easy with Excel solver function. So let's just do it. It will just take us a couple of seconds actually. We go to data ribbon, solver, and we basically, let me just go ahead and delete the ones that I already have here. Let me just redo all of them, and then this one. Okay, so let's start with the objective function. Our objective function is to maximize this. Awesome. So which has inside of it this formula here. Perfect. So you guys can see here. Next is, well, is it a maximization, minimization? It's a maximization. Next is by changing which cells? By changing these three cells. Perfect. Next is the constraint. So let's start adding the constraints. The first constraint we want to add is this one, that the sum should be less than or equal to 1000, but that's easy. So this cell, we want to make sure it's always less than or equal to 1000. Can't be easier than that. Add the next constraint. The next constraint is that it is basically the second constraint, that this number do not exceed 40,000. That can't be easier either. And then we have one last constraint, which is that the third one, the content of this cell, which is basically giving us this formula. This is what is inside that cell. You can see it here clearly. It has to be less than or equal to, again, $150,000. Now, we don't need to add the remaining constraint because, let me show you why. Because if you remember, by just clicking here, it's already making all three variables greater than or equal to 0. But if you were to forget and you added those, it's also doable. So all you do is you just add. The cell reference would be this one. Make sure that one is, select the correct inequality. This one is greater than or equal to 0, and so on. Add that. Okay, let's just do it regardless. This one is greater than or equal to 0. And finally, at the last one, the third one is greater than or equal to 0. That's it. So we have 6 constraints. The last 3 are the redundant ones, because by just checking this, you can easily accomplish that. So let me just remove that, I guess. And now let's see if when we press solve, if we get the correct answer. So something that I failed to mention earlier, there's this really 3 different choices for solving the problem. Usually the nonlinear optimization will do the trick, but because our problem is a linear programming problem, it might be also useful that, well, we can as well solve it using the simplex method as well, which is actually more efficient in this one. But anyhow, I'll just keep this one, which we're not gonna change it. So I just press solve. And continue. Solver paused. Current solution values displayed on. Sorry. Continue. Okay, there you go. Okay, I just changed one of the configurations, so maybe I should have mentioned that as well. Let me show you what I changed while I was preparing for this lecture. I just went inside this and I changed this option, show iteration results. Probably I shouldn't have done that, but you guys can see that I had to press OK 3 times. So basically by our starting point, we got to the desired result in 3 steps. All right, so in 3 steps we were able to constrain precision. Our precision is this much. It's extremely precise, 1 in a millionth chance of an error. So it is extremely precise, but this is usually annoying, right? So because the iteration took place in 3 steps, I didn't even bother checking what was the steps. If you guys want, actually, you know what? Cancel. Let's check what those are. So this is the correct answer, by the way. $114,560 is the maximum profit we can do, and this is how I should be allocating the land. In fact, let me just format it to a number. And even better, let's just, okay, so how many acres should be dedicated to each part? I'm trying to dedicate as much as I can to developing the land, but unfortunately it's not easy, right? So it turns out that this is the best allocation which satisfies all 3 constraints. And look at that, all 3 are satisfied with equality. That's perfect. All 3 results are positive, all 3, okay. So let me now go ahead and destroy this again. Let's see the 3 steps. So 200, 300, let me start with something which is probably efficient. 300, I meant to say, let's say 5, inefficient, I should say. 200, okay. So is this good, but definitely inefficient. Okay, starting from this point, let's see the iterations. All right, so data, remember, I just checked the options. I just clicked on this one, show iteration results, right? For all methods, we are showing the iteration result, but the accuracy is still the same. So the claim is that we can get to the final result in only in just a few iterations. This shows how powerful the algorithm we are using, basically. So press OK. All right. So these are the same thing. So let's see the result. Let's see how evolutionarily we will go to the desired answer, right? So first iteration, solve. Okay, solver paused and current solutions displayed, I don't see them. Okay, let's continue again. Oh, there you go. Okay, so this is the first solution, 443. Okay, we guys, we can even, well, you guys can use paper pencil to write down, but we started with I think, what was it, 500, 200, 300. In the first iteration, we came to these numbers. Now, we continue one more iteration, and look at what happened. The iteration gets closer to the desired answer, and then one more. Actually, we are done. In just 3 steps, we got the result. So one thing we can do is, we can even check these things. What we can do is keep solver solution, return solver parameter, outline the report. Let's see outline reports. Okay, press OK. Let's see if it gives us all the iterations. Is it doing anything? I'm not sure. It might be, or maybe not. No, it's not. But I think there must be an option where it's basically, no, I can't see anything. Where it shows basically the steps, so you don't have to use paper pencil to do it. But we got the correct result regardless, right? So this is a dollar amount that we, this is the maximum profit that you can get from conserving, farming, and developing this land. And I hope this was a useful example for everybody, and hope to see you guys in our next lecture.